Hey Geometry, Lesson 9, Scaling Principles for Volumes. If you remember, a few lessons ago we did scaling principles for area, and we discovered that our scale factor for area is squared between the area of two similar figures. So now we're going to talk about volumes. Let's do a little discovery first. So for each pair of similar figures, write the ratio of side lengths, A to B or C to D, that compares one pair of corresponding sides. Then complete the third column by writing the ratio that compares the areas of the similar figures. Simplify the ratios when possible. So this first one was done for you. We have 6. Now let's do this. 6 to 4. And we also have 3 to 2. Then if you look, our ratios of areas, the area of this triangle is 1/2 times base times height. That's 16 times 1/2, 18 times 1/2 is 9. And this one is 1/2 times base times height. That's 8 times 1/2 is 4. That's how we have our ratios to areas. And then notice that it is the same as those two numbers squared. 3 squared to 2 squared. And I'm equating that back to the most simplified ratio of sides squared. And you'll see the pattern as we go. Let's look at rectangle A and rectangle B. They're similar. So first we compare the sides. We have 3 to 15 and 1 to 5. If I calculate the area, 1 times 3 is an area of 3. 5 times 15 has an area of 75. If I simplify that to the most simple form, 1 to 5 is comparing your area, which I can equate it to my most simple scale factor, comparing sides squared. See the pattern? Here you have another set of triangles. So I compare 4 to 2 and 10 to 5. 2 to 1 is reduced, so 4 to 2, 10 to 5, that's reduced. If I calculate the area of triangle C, 1/2 base times height gives me 20. Triangle D, 1/2 base times height gives me 5. If I reduce that, I get 4 to 1, which is the same as 2 squared to 1 squared, which is the most basic side, scaling reduced. Okay, last two, I believe. 2 more triangles, comparing your side lengths, your height, your base. If I reduce that, so 4 to 12, 6 to 18, 1 to 3, calculate the areas. 1/2 base times height gives me 12. 1/2 base times height gives me 108. Reduce it, and that's the same as, like, 1 to 9 is the same as 1 squared to 3 squared, which is my most basic comparison of the original single dimension shapes, sides, single dimension, either height or base, reduced. So as you see, I've got my scale factor, and then I square it to compare areas. Okay, with rectangles, I have my scale factor, 1 to 2, and then I square it for my scale factor of areas. Make sense? All right. State the relationship between the ratio of sides A and B and the ratio of the areas. Well, when the ratio of the side lengths is A to B, then the ratio of the area is A squared to B squared. Make a conjecture as to how the ratio of sides A to B will be related to the ratio of volumes, S to T. So if my ratio of side lengths is S to T, then I bet my volumes then the ratio of volumes will probably be S cubed to T cubed. Area is two-dimensional, and the comparison of the areas were squared. Since volume is three-dimensional, the area, or the comparison of the volumes, will probably be raised to the third power. That's my conjecture. What does it mean for two solids in a three-dimensional space to be similar? For two solids to be similar, I should be able to do a sequence of basic rigid motions like reflection, translation. So that would allow me to map one figure onto another, and dilations. Okay, similar means that I can do basic rigid motions and dilations to map one figure onto another. Okay, now let's talk about three-dimensional. And first we're going to look at the ratio of side lengths, A to B, and then talk about the volumes of the similar figures. Okay, simplify ratios as possible. This is the same thing we did with our two-dimensional shapes, except now we've got 3 dimensions and we're going to talk volume. Cool? Okay, so first we're going to compare our side lengths, 5 to 4 and 10 to 8, which you see right there. I'm always going to look at the most simplified comparison of single dimension in our similar figures, because it's going to relate back to our volume column. So if you remember, volume of a cone is 1/3 pi r squared h. That's a cone. So that's what I used right there to get my volume of the bigger cone compared with my volume of the smaller cone. Go ahead and reduce it, which means I can cross that off, I can cross that off, and I'm left with 250 compared to 128. Divide by 2 gives me 125 to 64, and I have a few perfect cubes there. So that right there, and you can see I can relate it back to my my single dimension comparison of lengths. We'll see a pattern here. Now I'm going to compare all three height, width, and length of a rectangular prism. 2 to 10, 3 to 15, 1 to 5. 1 to 5 is the most simple comparison of side lengths. Go ahead and calculate your volume. Length, width, and height gives me 6. Length, width, and height gives me 750. Go ahead and simplify that. If I divide by 2 and then I divide by 3, I'm left with 1 compared to 125, which those are both perfect cubes. And then I can compare that back to my most basic comparison of single dimension side lengths. Okay, what we see finally here is my comparison of volumes will be the most basic side length cubed. This is my scale factor. Okay, so our scale factor, I can cube it, and that will give me my scale factor for the volume. Okay, so go ahead and push pause and look through the measurements of all the lengths and calculate your volume. Here is a triangular prism, so I've got 1/2 base times height times the height of the prism, so it's like area of the triangle times the height of the prism. Divide by 144, I have perfect cubes. And the last two. Okay, we always end up with comparing our volume, which would be our scale factor cubed. Okay, comparing our volume, which is our scale factor cubed. So use the triangular prism shown below to answer the questions that follow. Calculate the volume of the triangular prism. I have volume equals, there we go, it's a right angle, so 1/2 times base times height, that's the area of the triangle, times the height of the prism. So 3 times 3 is 9. 9 times 5 is 45. So we're at 45 over 2 units cubed. If you wanted that in a decimal, that would be just fine. From one side of the triangular base, if one side of the triangular base is scaled by a factor of 2, the other side of the triangular base is scaled by a factor of 4, and the height of the prism is scaled by a factor of 3. What are the dimensions of the scaled triangular prism? So that's a right angle. And then we're coming straight up. So we have our original triangular prism. One side is scaled by a factor of 2. So I'm going to go 6 here. The other side is scaled by a factor of 4. So I'm going 12 there. And the height is scaled by a factor of 3. I'm going to go 15 there. So the new dimensions of the base are 6 by 12, and the new height is 15. Well, let's go ahead and calculate that. Calculate the volume of the scaled triangular prism. So volume equals 1/2 the new base, 6 times 12, and the new height is 15. That's a lot of numbers. Let me get my calculator. So 1/2 times 6 is 3, times 12 times 15 gives me 540 units cubed. So make a conjecture about the relationship between the volume of the original triangular prism and the scaled triangular prism. So the volume of the scaled figure is larger. I would say it's equal to the volume of the original figure multiplied by the scale factors. Let's try that. So our scale factors that they gave us, one side was a scale factor of 2, that's the base. The other part of the base was scaled by a factor of 4, and then the height was scaled by a factor of 3. That's 8 times 3 is 24. Our original volume was 22.5. So if I multiply that by my scale factor, what will I get? 22.5 times 24. Cool, it's 540. So these are my scale factors, which gives me 24, the product of the scale factors. If I multiply them by the original volume, I get the new volume. It's a lot of boxes on one page. Do the volumes of the figures have the same relationship as was shown in the figures in exercise 1? Well, no, because we had different scale factors. It wasn't just one scale factor. Each dimension was scaled differently. So it doesn't work the same as in exercise 1. So the figure was scaled differently in each direction. So the volumes are, oh goodness, are related by the product of each scale factor of the scale factors. And I'm underlining the S. So by the product of the scale factors. Okay. I use the rectangular prism shown to answer the questions that follow. Calculate the volume of the rectangular prism. So here we just do base times area of the base times height, which is just 8 times 12, 96 units cubed. Now we're going to scale it. if one side of the rectangular base is scaled by a factor of a half, so we're going to have a 4. 8 times 1 half equals 4. The other side of the rectangular base is scaled by a factor of 24. So I'm going to do the 1 times 24 equals 24. And the height of the prism is scaled by a factor of a third. So 12 times 1/3 equals 4. What are the dimensions of the scaled rectangular prism? Oh, the dimensions. I was going straight to volume. So we've got, I did it right up there, 4, 24, and 4. So our base, not drawn to scale, is going to be, it's not drawn to scale, but it can't be that bad. So I got smaller here and much deeper there. So this used to be 8, it's 4 now. This used to be 1, it's 24 now. And then we go from 12, losing it here. There we go. The height went from 12 to 4. So I'm at 4 by 24 by 4. So the volume, I'm going to multiply those. 4 times 24 times 4 is 384. Cool. Now my original volume, I'm taking this off. The original volume was 96. And then if I multiply it by my scale factors, which is 1/2, 24, and 1/3, what do I get? 96 times 1/2 times 24 times 1/3. 384. It's magic, right? Not really. Make a conjecture about the relationship between the volume of the original prism and the scaled prism. I sort of messed up. I can't do a conjecture when I just showed you what the relationship is. You multiply the area by the product of the scale factors. So last question. A manufacturing company needs boxes to ship their newest widget, which measures 2 by 4 by 5 inches cubed. Standard size boxes, 5-inch cubes, are inexpensive but require foam packing so the widget is not damaged in transit. Foam packaging costs 0.03 cents, 3 cents per cubic inch. Specially designed boxes are more expensive but do not require foam packing. If the standard size box costs 80 cents each and the specially designed boxes cost $3 each, which kind of box should the company choose? Explain your answer. So let's look at the foam packing. Let's see, our volume is 2 by 4 by 5. 8 times 5 is 40. So that'd be the volume of the widget. Then we have the 5-inch cube boxes. So I've got the box is 5 times 5 times 5, a bit large, 125 inches cubed. So 125 minus 40 is 85. And that's how much packing material I would need, is 85 inches cubed. I would need that for packing material. So how much does that cost? Okay, the packing material times 0.03 is $2.55 each. So $200.55 just of packing material, but my box which is 80 cents. The total cost there would be, 2.55 plus 80 cents, $3.35 for the inexpensive box plus the packing material. Okay. And then we have the specially designed boxes are $3 each. So the specially designed boxes are only $3. The cheap boxes plus the packing material are $3.35. So the specially designed boxes are more efficient. They cost less. I would buy them. Cool. All right, we'll try some problems in the morning. Good job.